Welcome to this video. In this video we are going to discuss about differentiator circuit using operational amplifiers. A differentiator is nothing but an operational amplifier circuit used to get the derivative of an input waveform at the output terminal of the circuit. The basic circuit diagram is shown in the figure. Here the input is given to the inverting input terminal of the operational amplifier. And it is similar to the basic inverting amplifier, with the only difference that the input signal is connected to the inverting terminal through a capacitor C1 instead of a resistor R1. In the basic inverting amplifier circuit, instead of C1 we have an resistance R1. Here we have replaced the here in the inverting amplifier configuration we have replaced the resistor R1 by a capacitor C1. By using the Kirchhoff's current law at the terminal or at the node V2, we can write the current By using the Kirchhoff's current law at the terminal or at the node V2, we can write the current IC equal to IB2 plus IF. Here IB2 is the current flowing into the operational amplifier and IF is the current flowing through the feedback network or the feedback resistor RF. But by assumption we know that no current will flow into the operational amplifier due to the infinite input resistance. So we can take IB2 equal to 0. So IC will be equal to IF. Also we know that the non-inverting terminal is connected. Since the non-inverting terminal is connected to the ground, there exists a virtual ground at the inverting input terminal. So we will get V1 equal to V2 equal to 0. From the circuit, we can write the current IC as IC equal to C1 into dVc by dt, where Vc is the voltage across the capacitor, that is equal to C1 into d by dt of voltage across the capacitor is V input minus V2. Since V2 equal to 0, we get it as IEC equal to C1 dV in by dt. Similarly, the current through the feedback network IF equal to V2 minus VO divided by RF. Since V2 equal to 0, we get IF equal to minus VO divided by RF. So by equating these two currents, we obtain C1 dV in by dt equal to minus VO by RF, or the output voltage VO equal to minus RF C1 into dV in by dt. So the output voltage is the derivative of the input voltage V in multiplied by minus RF C1. So the negative sign shows that the output and input waveforms are out of phase. This figure shows some of the outputs of the basic differentiator circuit. If we give a sine wave at the input terminal, we obtain a cosine wave at the output, and these two waveforms are out of phase. Similarly, if we give a square wave at the input terminal, we obtain a spike at the output terminal. The second circuit shows the practical differentiator circuit. Here the difference is that here we have added two extra components R1 and CF to the circuit to avoid some problems, stability problems as well as high frequency roll-off problems. Here a resistor R1 is added in series with the capacitor C1, and a capacitor, feedback capacitor CF is connected parallel to the feedback resistor RF. These two components are added to avoid some stability problems as well as to reduce the high frequency roll-off problems.